Okay, so now what we're going to do is we're going to finish up section 9.3. We already did a hypothesis test for section 9.3. So now what we want to do is we want to talk about how to work with a confidence interval as well. Okay, so just like what we did when we worked on confidence intervals for proportions, we're going to have the same criteria for confidence intervals with means. All right, if our confidence interval does not contain the hypothesized mean from the null and alternate hypothesis, then we're going to wind up with the conclusion of reject your null hypothesis. If it does contain the mean, then you would fail to reject the null hypothesis. Again, these have to be an equal, not equal. It has to be a two-tailed test in order for this to work. So if we look at this example, at the Hawaii Pineapple Company, the mean weight of the pineapples harvested from one large field was 31 ounces last year. A different irrigation system was installed this field after the growing season. Managers wonder if this change will affect the mean weight of the future pineapples grown in the field. To find out, then they select and weigh a random sample of 50 pineapples from this year's crop. Okay, so we want to state our hypotheses and define our parameter of interest. Null hypothesis, we would be getting mu equals 31. Alternate hypothesis, we would be getting mu is not equal to 31. Okay, where mu equals what? The true mean weight in ounces of all pineapples grown in the field this year. Okay, we want to check our conditions. So our conditions are going to be the same exact conditions we had to use for the last chapter. So in section 8.3, we did conditions and we did the formula. So if you need the conditions or you need the formula, you can go back and refer to everything for section 8.3. All right, our conditions, we need to have random. All right, which yes, we met random. It's a random sample. Of 50 pineapples from this year's crop. Right? Remember, you need to make sure that your random sample is coming from the population of interest, right? It could be that we're looking for this and then somewhere they say like we're going to take a random sample of 50 pineapples from a neighboring field. Well, that's not right, okay? It's not the right parameter, so we got to be careful with that. The 10% condition, right? Our population is at least 10 times our sample size. You need to make sure, a lot of you guys struggled with this on the last test, and this is critical. You cannot just put 500 here, okay? You need to show 10 times 50 is at least 500, okay? You have got to show where that 500 comes from. And this is not my criteria, this is the College Board's criteria. And this is the criteria that we have discussed many times in class. All right, and it's critical, and you've got to make sure that you're doing this right, okay? All pineapples in the field. Okay, and so we've met that condition. You also need to make sure for your large counts. Some of you guys last test just wrote since n is greater than 30. Nope, you have to say since n equals 50, and that's greater than or equal to 30. You have to state what your sample size is when you're working on your large counts condition as well. That means it's okay to use the T-star procedures. All right. Now, for this particular problem, they're giving us the interval. So they've already provided it for us, but you need to make sure that you're comfortable with creating that, just like we did last chapter. Okay, and now let's talk about what kind of conclusion we can make. So this year we found that the interval would be 31.255 to 32.616. So we're trying to figure out how it relates to 31 back from our hypotheses. So when we're looking at that, we would say since the 95% interval, oops, I forgot the word interval, sorry, interval does not contain 31, we reject the null hypothesis. Which means what? we have convincing evidence that the true mean weight of pineapples, oh my goodness, how can I spell weight? Oh, there we go. Weight of pineapples grown this year is not 31 ounces. All right. It could be that you're asked to do a hypothesis test with coming up with your own interval, but it could also be that you're given an interval and you just need to make a conclusion. Okay, and so we can chat more in class. Of course, we'll practice some, but you've got these guys. All right, and we've got that as our answer. So next up, okay, we want to look at how to work with paired data. So sometimes this is going to be called a matched pairs t-test. Sometimes it's just going to be called a paired t-test. They mean the same thing. Okay, this is when we have data that's as an ordered pair. Okay, if we have data of an ordered pair, what we're going to work with is we're going to have mu sub d. So it's a regular mu with a little d, which means the mean difference between the 2 points in an ordered pair. All right. So when we've got a problem like this, for their second semester project in AP Stat, Luke and Abby decided to investigate which line was faster in the supermarket, the express lane or the regular lane. To collect their data, they randomly selected 15 times during the week, went to the same store, bought the same item. However, each time one of them used the express lane and the other used the regular lane. To decide which lane each of them would use, they flipped a coin. If it was heads, Luke used the express lane. If it was tails, Abby used the express lane. They entered their randomly assigned lanes at the same time and recorded the time in seconds it took them to complete their transaction. We want to carry out a test at the 5% level of significance to see if there is convincing evidence that the express lane is faster. So the first thing we need to think about is, like, what does it mean for the express lane to be faster? That would mean that these times are lower, okay? Right? So your express times would be smaller than your regular times. So what we need to do is we need to really think about that idea, right? If we have regular minus express, right? If that gives us a positive result, means that the express lane was faster. Okay, because then this would be smaller and you would get a positive answer. Okay, a positive result. So what I've done is I've actually subtracted mine, and I set mine up here. These are regular minus express. So 342 minus 337 is 5. 472 minus 226 is 246. But an important thing to remember, right, is that that's annoying to do, because what we're going to eventually need is we're going to need the average of all of the differences, and we're going to need the standard deviation of all of the differences. So I just want to recap a skill that we've had before. I have already typed in my express and my regulars just to make the video a little quicker. Okay, be careful when you're naming this. If you just try to call this EXP or EXPR, it's not going to let you because they are known as other commands within the calculator. So I had to type out the entire word express. So what I can do here is I can call this my differences. So if I call it DIFF, all right. And what I want to do is in this cell, my equation cell, I'm going to type in reg minus express, PRESS, boom, and it subtracts them for me. Okay, so I did regular minus express, and that's where I got my column of data. Then I could very easily do one variable statistics of this column of my differences, and that's where I got my mean difference and my standard deviation of my differences. Okay, you're still going to just use S because it's a sample. All right, and we've got that there. So what we need to do is we need to now set up our hypothesis test with our phantoms. Okay, so we're going to begin with our parameter. We are going to let mu sub d equal the true mean difference of regular minus express in time required to purchase an item at the supermarket. All right, hypotheses are going to look a little different this time. Our null hypothesis, if there is no difference, that means that regular and express are going to be the same. So that means that regular minus express would be equal to 0. Because if they're going to be the same, then when you subtract them from each other, they're going to equal the same number. So we would have the mean difference is equal to 0. Or the mean difference, and this is why we had this conversation back up here. If we set it up as regular minus express, we would get a positive result, means that the express was faster, which means that it would be positive. Now, you have to write down how you're subtracting, here, here, or somehow, because otherwise this has no context and makes no sense. If you chose to do express minus regular, that's fine. That would mean that a negative result would be meaning that express was faster, and you would have this as a less than 0, or a negative value. Okay, those of you who like words, you could write express was faster, right? And this is no difference for the words. All right, our assumptions. We're gonna see if we can do a paired t-test for the mean. So random was met. Okay, they had times were random, times and lanes were randomly selected. Okay, we're going to have normal. We need to graph our data. And if we graph our data, come on. All right, there's no skewness. Perhaps we have one outlier, but we don't have any strong skewness. So when we're looking at our data, right, for our large counts, since n is less than 30, right, and our n was 15, then we need to check the box plot. Okay, we would sketch the box plot. You draw your box plot here, all right, that we've got right here. No strong skewness. Means it's okay to use T-star, right, or the T procedures. And then when we're looking at the 10% condition, well, the number of times you could do this is unlimited, right? So if we're talking about as our population, at least 10 times our sample size, at least 10 times 15. Yes, we have an unlimited grocery checkouts, right? So that's definitely going to be greater than 150. All right, we're running out of space. Sorry. So let's pare this down a little bit. Our name is a paired t-test for the mean difference. You could write difference if you want, or you can write mu d. Our test statistic is going to be t equals, we're still going to use the same idea. It's still x bar minus mu, but we're going to have x bar sub d minus mu sub d over the standard deviation of d divided by root n. We're using the same idea, we're just using the differences. So when we did one variable statistics, we got 42.7. The mean difference we're hypothesizing is this 0 back up here over 84.0 divided by root 15. And we're going to get 1.97. Oops, didn't mean to put the point there. Oh my goodness, I can't write today. So there's our t. All right, so now what we need to do is we need to check out our p-value. We're going to have a greater than test, right? So to obtain our p-value, we're going to have a right-tailed test. We're going to have our TCDF, of 1.97 to infinity. Degrees of freedom are going to be 14. Make sure you are stating what degrees of freedom you are using, which gives us 0.034 is our p-value, because our normal curve would have a 0 and a 1.97 from our test statistic, and it would be above to the right, which is why I did this type of shading on this part. Okay, which means now we need to make our decision. All right, we're going to compare our p-value to our alpha. Our p-value is 0.034. Our alpha was 0.05. That's less than, which means we reject the null. Remember, all of this is necessary. So now if we conclude there is convincing evidence that the express lane was faster than the regular lane. On average. Okay, good job. Make sure you tested out the calculator stuff. Okay, practice subtracting it. I mean, it's so much faster because, I mean, you could subtract them all and then just type this in by hand. So you could subtract them all by hand and then just type this in, or you can type this in, and let it subtract for you. It might come out in the wash as even, you know, and that it doesn't actually have a difference, but it might come out as a difference. And remember, you need to graph your t-distribution, however that would go. Okay, good job today.